with its twin branch, which is the estimation process. So every researcher, statistician, or user of statistics, engage in statistical modeling or statistical analysis would definitely require the use of a problem at the end of you will not be able to. This lecture will be of importance to whoever is going to be using.
Mr. Mohammed, can you hear me?
Yes.
Mr. Mohammed, can you hear me?
Yes, I can hear you.
Please, your students are complaining that your microphone is too low. Is there any way you can adjust it to make it louder?
Hello?
Yeah. Yeah, I think it's better now.
It's better now. Like, can you try to speak like a little bit more loudly, or maybe adjust your microphone?
Can you hear me now?
Yes.
Yeah. Yes, we can hear you now.
Okay, can you hear me now?
I think it's better now.
So, presentation is prepared by myself, Dr. Anita, and Abishra Mashkur. So, my slide here is not moving. Okay.
It should be with you. Yeah.
Yes, yes. So, as I was saying, I said it is important that whoever will be using statistical procedures, or every user of statistics, including those using machine learning, must have the basic ideas of the processes one must follow in writing an hypothesis. So it is on this note that this workshop is important, particularly as we are going to be talking about the use of hypotheses in machine learning. So at the end of this presentation, we expect that participants should understand the definitions used in hypothesis testing. We objective hypothesis, as well as you should be able to decide on the appropriate statistical tests for hypothesis testing. We also want to, show you how you can use the statistical online calculator to perform some your hypothesis testing. And also, you should be able to interpret the result of hypothesis testing and write an informed decision. We also expect that at the end of this presentation, you should be able to explain the relationship between type 1 error, type 2 error, and the power of the test. As a way of introduction, we all know that, always, for instance, if a scientist might want to know whether the earth is warming, a physician may as well want to know if a particular drug, increases blood pressure or reduces blood pressure. Also, a teacher might want to see if a new techniques for teaching is better than the traditional one. So all these are questions that researchers want to address. And this can be addressed using statistical hypothesis. Now, whenever you are confronted with problems that require answering questions, there are procedures you must follow for you to be able to, arrive at a conclusion. And the process of hypothesis testing, a researcher must first define the population under study. You should be able to state the particular hypothesis that will be investigated. And then it should, give the level of significance, as well as select a sample from the population. The researcher should also be able to collect data from the sample and then perform calculation required for the statistical test and then reach a conclusion. So basically, the process of hypothesis testing follow these 7 steps. So before we go into the processes, let's look at some basic definitions. The first is statistical hypothesis. It is just a conjecture about a population parameter. And people will tell you it's a claim or a guess. So what is important is whether this test or this claim can be tested. And if it is tested, can it be true or not? So a conjecture about a parameter that can be true or not is what is referred to as a statistical hypothesis. Then we also have what we call the null hypothesis, which is conventionally symbolized by H0. It is an hypothesis that states that there is no difference between a parameter and a specific value, or no difference between 2 parameters. So it is also referred to as an hypothesis of no difference. Then we have what we refer to as the alternative hypothesis, symbolized with H subscript 1 or H subscript A. It is a statistical hypothesis that is the opposite of the null hypothesis. It tells you, yes, that there are existence of difference between 2 parameters, or between a parameter and a specific value. So whenever you are confronted with questions or research work, you should be able to understand these basic concepts, these definitions. You should be able to know which is your null hypothesis and then which one is your alternative hypothesis. So the 2 must be different, and it is because of these different opposites of one another that your questions will be able to be answered whichever way you arrive at a conclusion. So how do we formulate hypotheses? We have different scenarios here that we've given. You look at the first example. Here is a researcher who is interested in finding out whether a new medication have any undesirable side effects on patients. The researcher is particularly concerned on pulse rates.
Mr. Mohammed, please.
Yes.
People are still complaining that your voice is too low. Can you make it louder, please?
Okay. I hope you can hear me now.
Yeah, better.
So the researcher is particularly concerned about pulse rates of patients who takes medications. He wants to know if after taking these medications, the pulse rate, whether it increases, decreases, or it remains unchanged after taking this medication. So we want to see how we can formulate an hypothesis to reflect this kind of question. So if you look at this question, you will see that the researchers knows that the mean pulse rate of the population is 82 as given in the question, 82 beats per minute. So for you to state this hypothesis, as we said the null hypothesis is usually what is known. And from the question, it is stated clearly that the pulse rate is 82 beats per minute. So if you are going to state your null hypothesis, it is that H naught is such that mu is equals to 82 beats per minute, versus the alternative hypothesis as mu is not equals to 82 beats per minute. So clearly, if you look at this, you can see that the null and the alternative hypothesis are opposite to one another. So the null hypothesis specifies that the mean will remain unchanged, while the alternative hypothesis states that it will be different. So if you have this kind of questions where you are not clearly stating whether you want to find out if it is an increase or a decrease, then this type of test is a two-tailed test. Clearly, if you look at the question, you will see that the researcher's interest is to know if the pulse rate will either increase, decrease, or remain unchanged. So it is because of this that this hypothesis is referred to as a two-tailed test. We also have another example where a chemist who wants to invent an additive to increase the lifespan of a battery. The lifespan of this of normal battery without additive was found to be 36 months. This chemist wants to state an hypothesis to reflect this question. So how does he do, or how does he go about that? Clearly, if you look at the question, you will see that the interest of this chemist is to increase the lifespan. So if you want to state the hypothesis, you can state it as it is stated there, that H naught is such that mu is equals to 36 versus the alternative hypothesis, which is equals to mu is greater than 36. So in this situation, the chemist is only interested in increasing the lifespan of the battery. So the person's alternative hypothesis is that the mean is greater than 36 months. Okay, so because of this alternative hypothesis that was reflected from the question, that this chemist wants to increase the lifespan of his automobile battery, clearly this is a right tail test. Okay, and so on. We also have for a left tail test, where you have the alternative hypothesis being less than the null hypothesis. So if you look at this question too, we have a contractor who wishes to lower the heating bill by using a special type of insulation in houses. The average of the monthly heating bill is $78. So this contractor wants to reduce the heating bill for the insulators in his house. So this is how you can state this kind of hypothesis. And for the fact that the null hypothesis is less than equals to 78, this is a left tail. Yeah, so these are different scenarios for formulating hypothesis. The first important step is be able to state your null and alternative hypothesis. So if you have an hypothesis, like the first example, where you have your mu to be equals to 82, and the alternative hypothesis is that the mu is not equals to 82. This is a two-tailed test. but the one where you have the mu being greater than 36 for the alternative hypothesis, it is a right tail test. And finally, we have the left-tail test, where the mu here is less than $78. So these are different scenarios you have for formulating an hypothesis. So we have a table here for different types of tests and how the null and alternative hypothesis can be stated. So the first one is, I hope we are together. Hello?
Yes, and we are with you. I'm with you.
Yes.
But if you can make your voice louder, our person I will appreciate it.
Okay.
We are all here, but from my hand, I can hear you very well.
Okay.
I can hear you loud and clear.
Thank you very much. Now, the different type of tests and how the null hypothesis and the alternative hypothesis can be stated, we have it presented here on this table. For the two-tail tests, we said the null hypothesis should always be that your mu is equal to either the specified value or the second parameter. In this case, we are using mu naught, which could be a specific number. Okay? Then the alternative hypothesis for a two-tail test is such that mu is not equal to mu naught. So if you have a two-tail test, from your question, this is how you can state the null and the alternative hypothesis. And this test is for any significant difference, whether it is increase or decrease, or it's remain the same. Then we have the right tail test. For the right tail test, the null hypothesis is such that mu is equals to mu naught, or mu is less or equals to mu naught. Okay, so any of these can suffice for the right tail test. You can decide to use just the first one, which is mu is equals to mu naught, and then proceed to write the alternative hypothesis, which is mu is greater than mu naught. This is for a right tail test, and it is used if the sample mean or the statistic is greater than the hypothesized value. Then we also have the left tail test. And for the left tail test, what we have is the H naught is such that mu is equal to the mu naught, or the H naught is such that mu is greater or equal to the mu naught. Why the alternative hypothesis is mu is less than the mu naught. So this is basically everything that has to do with the specification of your null and alternative hypothesis for every type of test you are conducting. So we have an exercise here that we've decided to project so that participants would practice it or look at it after the presentation because of time. Then after, stating your hypothesis, another important concept is the level of significance. When you are able to write the null and the alternative hypothesis, the other thing is to state your level of significance. The level of significance is a fundamental concept in statistics that measures how much risks of error we are willing to accept in a statistical decision. It defines the threshold for rejecting the null hypothesis, and it helps to control the probability of making a type 1 error. So the level of significance is just the risks you are willing to accept after coming up with your conclusions or making your inferences. So that risk, you want to set it so that you'll be guided by it, so that at the end of your research, whatever you are coming up with, you should be able to have a certain level of confidence to say that, okay, my results, I am confident that I have so percentage of confidence that this result is correct. So, and how do you do that? Is with the help of the level of significance. So it is usually what you arbitrarily fix. And the common choices for this alpha is 0.10, which is 10%. That is to say, you are willing to risk 10% error, or you can use 0.05 for 5% and 0.01 for 1%. So we have an interpretation for this level of significance for different alphas. So like we said, if you have 0.1, what you are trying to say is that you want a 10% chance of type 1 error. And it implies that you are having 90% confidence level for your results. So also, if you are talking about 0.05 as your alpha, you are saying you have 5% chance of type 1 error, and that you are confident you have 95% prediction or whatever you are carrying out. And then if it's 0.01, then you are 99% confident. So the choice of alpha depends on how strict you want to be in your decision making. The most standard alpha that conventional for most researchers is 0.05. Okay, but we encourage those who work in the health sectors and those in biostatistics to use the 0.01 because you are dealing with human life. So we want to be strict as much as possible so that whatever decision you are making, you should be, be strict about it because life is involved. So a smaller alpha makes it harder to reject H0, meaning you require stronger evidences from the data to be able to do that. So in hypothesis testing, alpha defines the critical region, that is the risks, the error you are willing to give up. So if after setting your alpha, how do you decide? Use what we call the p-value, which is in full probability value. So anytime your p-value is less than alpha, you always reject the null hypothesis. But if your p-value is greater than alpha, you do not reject the null hypothesis. So when interpreting results, it is important that you follow this statement strictly, because when some people were writing a conclusion, anytime they have their p-value being greater than alpha, they tend to say, okay, you accept the null hypothesis. No, it is wrong. The statement should be that you do not reject the null hypothesis. That is the conventional way of writing. But if your p-value is less than, if it's less or equals to alpha, you reject the null hypothesis. So the relationship between alpha to type 1 and type 2 errors. So just like we've said, type 1 error is just the risks you are willing to give up. So it is described as when you reject the true null hypothesis. Of course, that is what you want to do. And it is controlled by the level of significance, alpha. Then the type 2 error is what determines It is just when you fail to reject the null hypothesis, a false null hypothesis. And that is what defines the power of the test. So it is controlled by the statistical power of the test, which is 1 minus beta. So when you try to lower alpha, a lower alpha reduces the risks of type 1 error, but may increase the chances of type 2 error. That is, when you fail to detect, failing to detect the real effect. So this table is a guide for us to see how the relationship between type 1 error, type 2 error, and alpha. So now we have looked at how we, can write our hypothesis, the null and alternative hypothesis, and we've seen what the alpha is and the most common type of alpha to use. The next thing is test statistics. A test statistics is a standardized value that is computed from sample data and is used to determine whether or not to reject a null hypothesis. So after stating your hypothesis, choosing your alpha, the next thing is to subject your data to statistical tests. We have different type of these tests, and we decided to pick a few of them because we are trying to see how we can whet our appetite on this workshop. So the first one is the Z-test. The Z-test is one of the test statistics you use, and it is used when you have a question where you have a known standard deviation. A known standard deviation, that is to say, if you know the population standard deviation, then you are supposed to use the Z-test. In this case, you must know the population standard deviation, and then the distribution must be normal, and your data, your sample must be large. Then it is pointing towards the use of a Z-test. But if you have a situation where you don't know the population standard deviation, then you are required to use a t-test. So the t-test is used when the population standard deviation is unknown, the sample is small, particularly if it is less than 30, then you are required to use the t-test. You also have another test statistics, the chi-square test. It is used for categorical data when you want to test for goodness of fit or independence of samples. And then we have the F-test for comparing variances, or you want to use to compare more than 3 means. When you have more than 2 means, you want to compare if there are significant difference, then you have to use your F-test. And this is where ANOVA comes into place. You also have another test statistic that is Z-test for proportion. Okay, it is used to test one sample proportion. You want to see if from a particular sample, you want to check if certain claim is justifiable, then you have to use the Z-test for proportion. Now we have examples for different tests, and we've attached a video clip of which we may not be able to, show it to you clearly, but we've, pasted a link where you can easily go to the online and watch how this type of question can be solved using machine learning, particularly Python. So this is an example of a t-test. Here we have a young boy who establishes a mean time of a young boy who establishes a mean time of 16.43 seconds for swimming the 25-yard free time with a standard deviation of 0.8. Now, his father wants to know if he decides to introduce a goggle for this boy. He wants to know if this boy will be faster. So it is because of that he bought a goggle and decided to subject his boy for 15 rounds of this 25-yard swimming. And at the end of the day, he got a mean time of 16 seconds. Okay, so he wants to know if actually the boy was faster. So this kind of question can be solved using hypothesis testing, and you can also do that using machine learning and Python. So we've attached a video there for you to look at the procedure when solving this kind of question using machine learning. So this is the solution. Like we've said, when you have the question like this, first thing is to state your hypothesis, at least after writing out every information from the question. On the question, if you look clearly, you'll see that we are giving our standard deviation to be 0.8 seconds. That is to tell you that we have a known population standard deviation. So because of this, clearly we are supposed to use a z-test. Our sample size is given as 15. Our sample mean is 16. And our alpha is given to be 0.05. So by the time we state our hypothesis, and if you look at the question, the null hypothesis is saying that mean is equal to 16.43 seconds, while the alternative is less than 16.43 seconds. This is because the father wants to know if these boys swim faster. So if he's going to swim faster, that means the time has to be less. It is because of that the null hypothesis is mu is less than 16.43 seconds. So after we've established that we are going to use the z-test, the next thing is to substitute our values into the formula for z-test. And by the time you do that, we arrive at an approximate value of minus 2.09. And when you compare this with your critical value, using a left test at alpha equals to 0.05, you have a value of 1.643. So when you compare these two values, the critical value with the tabulated value, you see that the critical value, the tabulated value is greater. That is, the calculated value is less than the tabulated value. So because of that, we have to reject the null hypothesis. So also your p-value, by the time you use your online calculator, from the online calculator, we also have a video clip for you to see how it can be used. By the time you input this given data from the question, you have a p-value of 0.01. And when you compare it with your alpha, you see that it is less than 0.05, which is consistent with when you use the normal test statistics and the tabulated value. So, hello? Are we together? Hello?
Yes, we are
Yes,
still there. We are
yes,
still
yes,
there.
we are.
Yes.
We are
Yeah.
here.
So,
Can you
since
can you
we are
share
together.
that link in the chat so participants can see how it looks like?
okay,
Let
don't
them
know.
try one question with you.
If I try to copy this link now, I think it's going to take our time. So maybe
Okay. Okay, fine. You decide. I leave it to you. Fine. Proceed.
Yeah,
Sorry,
you
sorry
can
to
put it in
disturb.
the chat after your presentation. Put it in the chat.
Yeah.
Can you continue, please?
Yes, my screen is
Yep, you can continue. We will share all the materials with you after the workshop, including the videos and the lectures.
okay, I'm not seeing my slide again. Are you seeing the slide over there?
Yes,
We can see. Yeah, we can
We
see.
can see it. We can see it.
But I'm not seeing it. Okay. Okay.
Everything is in order, sir. We can
All
hear
right.
you. We can see the slides.
Okay, so clearly we are talking about the p-value, and we said that we have a p-value that is less than 0.05. So anytime you have, after comparing your p-value with your alpha, whenever the p-value is less than the alpha, which is the significant level, you are required to reject the null hypothesis. Okay, so if you are rejecting the null hypothesis for this question, then you are to conclude that at the 5% significant level, please, you have to clearly state this. You have to state the level at which you are concluding at, so that whoever is looking at it, we know what you are talking about. So the conclusion is at 5% significant level, there's no sufficient evidence to conclude that Jeffrey's mean swing time with the new goggle is faster than 16.43 seconds. So this is basically the steps you must follow in solving or approaching hypothesis testing. Now we also have another question, another example on one sample proportion test. Here is a mortgage department of a large bank that is interested in the nature of loans of first-time borrowers. This information, they want to use this information to, to tailor their marketing strategy. There's an existing knowledge that 50% of first-time borrowers take out smaller loans than other borrowers. And to perform a hypothesis test to determine if this percentage is the same or different from this 50%. With a sample of 100 first-time borrowers, they find out that 53 of these loans are smaller than other borrowers. So they want to test this hypothesis at 5% significant level. So this is another question on proportion. And then we have the solution, and then a link to how you can use the online statistical calculator to solve this kind of problem. So in this kind of question, you could see clearly that we have, from the given question, the sample size is 100, the success rate is 53, which implies that the proportion is 0.53. And given in the question, we have the level of significance to be 0.05. Clearly, the question is a two-tail test because you want to test the claim that the proportion of first-time borrowers who take these loans is equal to 50. So you want to take whether it equals or not. So because of that, this is a two-tail test. So by the time we apply our test statistics, which is the t-test or z-test for proportion, we arrived at a value of 0.60. The decision rule for alpha, if you look at the critical value at for alpha 0.05, you got plus or minus 1.96. And by the time you compare it with the tabulated value, we arrive at not rejecting the null hypothesis. So you do not reject hypothesis, the null hypothesis. If you compute these same values into your statistical calculator, you're going to have a p-value of 0.5486, which is greater than our significant level. So you can stick, you mustn't follow this procedure. Sometimes people stick to just the use of p-value. Okay, you can stick to the use of p-value and conclude your and make your inference. Okay, so for this question, our p-value is greater than 0.05. It therefore means that we do not reject the null hypothesis. So we conclude that at the 5% significant level, there's no statistical significance evidence that the proportion of first-time borrowers taking smaller loans differ from 50%. So this is another example of how a statistical testing procedure can be used using z-test for proportion. Now, we also have a one-sample t-test. As an example, where you have that the assumed mean SAT score of students admitted to General Hospital is 1,090. That is, the mean is 1,090, the population mean. The population standard deviation is unknown. The members of the biology department believe that students who measures in biology have higher SAT scores than the general population of students. So this is a t-test. Okay, it is a t-test because if you look at the question, you see that it is clearly stated that the population standard deviation is unknown. It is because of that we are resorting to the use of t-test. And this is a one-tail test because the researcher's interest is to predict that the biology students have higher SAT scores than the general population of students in the university. And what we have as the sample, we have sample size of 10 from that biology class and 1,176 for mean and a standard deviation of 131.86. They represent the estimate of the population mean score for this biology measure. So this question, clearly looking at it from the question, we could clearly see that it is a t-test and we would adopt our formula for t-test and do that. So this is how you go about it. You state your hypothesis, the null hypothesis, which is that mu is equals to 10,090, 1,090, and the alternative is greater than 1,090. So this is a one-tail test. So by the time you substitute those values into your test statistics, you arrive at an approximate value of 2.06. Now, for a t-test, you need a degree of freedom, which is the sample size minus 1, And because we have a sample size of 10, by the time you subtract 1 from 10, you have 9. And then you use that to look for your tabulated value. By the time you do that, you arrive at 1.833. So also, you can use your online calculator to get your p-value. For this case, our p-value is 0.033. And when you compare it with your alpha, which is 0.05, you see that it is less than alpha. So in this case, you have to reject the null hypothesis and conclude that at 5% significant level, there's sufficient evidence to conclude that biology majors have a higher mean SAT score than the General University mean of 1090. So this is how you solve questions involving hypothesis testing. So this is a practice question for participants to go and watch the video and see how they can. We provided the link also for you to, by the time you click on that link, you go straight to the video where you watch, and then as you are watching, you'll be practicing how you can use machine learning to, solve this kind of question. Now, another test statistics that we would want to discuss is the two sample tests. Now, the two sample tests, the test statistics for two sample tests can be the independent sample t-test or the paired sample t-test. Now, when you have two samples and you want to compare if their mean is the same or different, two samples from a different population, okay, you are required to use the independent sample t-test. But when you have a sample that you want to, a particular sample that is dependent on each other, but the data is collected such that it is collected over time. For instance, you want to collect data on student performance before and after teaching them a particular course. Now, you can decide to, give them a test. After writing the test, you mark the test, you keep the score on one side, and then you subject them to the teaching. After teaching them, you come back and give them another test. Now, after doing that, you have two different variables, but they are from the same people. So if you want to see if there's a difference in their mean, you use what we call paired sample t-test. So this is the difference between the independent sample t-test and the paired sample t-test. What does the paired sample t-test does, and what is it? And what is the independent sample t-test? The independent sample t-test is a parametric test. It's parametric because anytime you hear parametric, it means there are certain assumptions it must fulfill before you can use that test. So the independent sample t-test is a parametric test for two groups between participants design. While the paired sample t-test, also known as the correlated group test, it is also a parametric test, but for two within group participants or match participants, just like I've explained before. What does it do? For the independent sample t-test, what it does is to compare performance of two groups to determine whether they represent the same population or different population. But for the paired sample t-test or the correlated groups, they analyze whether each individual perform in a similar or different manner across different conditions. So that is the difference. And then for the independent, for the assumptions, the independent sample t-test, the data must be either interval scale or ratio. The distribution must be normal. You must have homogeneity of variance, that is the variance for the two samples. You are assuming they are the same. And then the observation must be independent. While for the pair sample t-test, same, the data must be interval to ratio scaled. It is also normally distributed. You are also assuming homogeneity of variances. But in this case, the observation is dependent or related. So we have an example here for us on how we can test for independent sample t-test. And we've attached a video clip for you to go and look at and see how you can practice from the video clip. Here is a researcher who wants to compare the maturity level of students who volunteer for a community service versus those who do not. So this researcher assumed that those who perform community service will have higher maturity scores than those who do not. So if you look at the table beside it, this is an experiment that was carried out for those who do not perform community service and those who participated in the community service. And this is what they find out. And how do you use, you can see that these are two different people. So they are independent. So because they are different set of persons, we have to use the independent sample t-test to know if the mean is the same or not. So this is a clip for you to go and look at it and see how you can use machine learning to solve this kind of problem. We also have a problem of pair sample t-test. So also is a researcher who is interested in participating in knowing whether young girls who participate in sports, they want to know if sports have a positive influence on their self-esteem. So these are a group of girls, and they were subjected to some starting self-esteem inventory of 50 before and after participating in sport over a 6-month period of time. And this is the result from the exercise attached there for you on the table, where you have before and after. So from this, you could see that by the time you use your pair sample t-test, clearly these are information from same set of persons, but at different point in time. This also, you can use your Python or machine learning to solve this kind of problem. And we have a clip for you to go through and practice. Now, this is an example of a t-test where you have participants who were asked to memorize a list of 20 words in 2 minutes. Half of these participants perform in a noisy environment and the others in a quiet environment. So if you look at this, these are two different people. So it is an independent sample t-test that can be deployed for this kind of question, because we are talking about two different environments for two different persons. And the dependent variable here is the number of words the participants are to recall. So if you look at this, you see that looking at this table, this is what was arrived at for those who were able to recall in noisy environment and those who do not, who were able to recall in a no noise environment. So clearly, participants vary within conditions. In the noise condition, you could see that the score ranges from 3 to 11. And for the no noise, it ranges from 9 to 18. So participant differs between the conditions too. Okay, so this type of question requires use of an independent sample t-test. And this is the report from the findings of this test. At the end of the day, it was discovered after, comparing the mean using our independent sample t-test, it was discovered that our p-value is less than 0. So all these things can be done through the use of the online calculator. Our p-value was found to be less than 0.001, and it was concluded that listening to noise affects short-term memory, at least in respect to word count. So we have so many test statistics. Now we are going to look at analysis of variance. It's also one of the parametric test statistics that is used for in hypothesis testing. It is used to see if there are any statistically significant difference between the mean of 3 or more groups. It calculates the ground mean, that is the mean of the means of each condition, and see how different each of these individual mean is from the ground mean. It premised on the assumption of t-test. Okay, the difference between ANOVA and t-test is that for ANOVA, you are just comparing 2 means. But by the time you have more than 2 means, then you have to move forward to ANOVA, which is analysis of variance. And we also have different ANOVAs. You have one-way analysis of variance. This is when you are comparing one categorical independent variable and one continuous dependent variable. For two-way analysis of variance, you're comparing 2 categorical independent variable and 1 continuous independent variable. And we also have multiple analysis of variance, where you are comparing 1 categorical independent variable and 2 or more continuous variables. Then you also have post-hoc tests. These are tests you want to find out or to locate where this difference in mean, where they lie. After conducting your analysis of variance, how do you know where this difference lies? You require the use of post-test. So we are not going so much into, because we are just trying to whet our appetite to have the concept, so that by the time you are using this test in machine learning, you know when to use any of them. Now, there are safety checks for ANOVA. Anytime you are carrying out analysis of variance, there are certain checks you must ensure your data fulfill. Number 1, it must be continuous parametric data, must be independent and identically, it must be independent and identically distributed. That's random sampling. Must be the variance must be homogeneous. Means you must assume equality of variance. So the Leibniz test sometimes identify problem here, but those posets and the well tests are often used to overcome this problem. You also have checks for maneuver. Also, you can use, must ensure continuous parametric data for independent variables. Must ensure that independent variables are categorical with 2 or more values. Also, the groups are independent of each other. They also ensure random sampling and random allocation. You must ensure adequate sample size. Distribution of the data must be normal. There must not be, you must not have an outlier. Then a linear relationship between each pair of independent variable. And also, there should be no collinearity. That is the dependent variable.
Mr. Mohammed, please, so that we can create time for question and answer.
And then
can you hear me?
Homogeneity of variance. Another test statistic is the chi-square, which is a measure of relationship or association that is developed by Kapelsin in 1900. It measures the association between two categorical variables. And then it compares the observed frequencies and expected frequencies. It determines whether two variables are independent. And then it allows us to find out whether groups, subgroups are homogeneous. Okay, so this is also a test statistics that you can use for your hypothesis testing. We have different type of this chi-square test. We have the one variable chi-square test, often referred to as the goodness of fit test, which is used when you only have one variable. Okay, then we have the chi-square test for independence, which is a 2x2. When you have 2x2, it's used when you are looking for an association between two variables with two levels. For instance, you want to see if there's an association between those who drink alcohol and those who do not drink, and those who smoke and those who do not smoke. So to use the 2x2 independent chi-square test. Then we also have the chi-square test for independence, the R by C. It's also referred to as the consistency test. It is used when you are looking for an association between two variables where one has more than two levels. So here, the difference between the 2x2 is that you only have two levels for both in 2x2, but for the R by C, you have more than two levels. Okay, we'll give an example here where you have heavy smokers, moderate smokers, and does not smoke. So these are different levels for this in this variables. And all this can be, tested using the chi-square test. Now we have our formula for chi-square. Hello, are we together?
Somebody is raising his hand.
Yes,
somebody.
we are together.
Are we together?
Somebody is raising his hand. Mohammed Rais.
Okay.
Yeah, so yeah, I think like as you mentioned, maybe leave some time for the questions. I don't know.
Okay,
Yes, try to summarize so that you can give time for question.
Yes, okay. How long do we still have?
Maybe you should have like 5 to 10 minutes more.
We've not gone far. We are supposed to spend at least 1 hour 30 minutes.
You have spent over 1 hour, sir.
Okay. So we have the formula for chi-square, as you can see there clearly. Then for one variable chi-square test, also known as the goodness of fit, like we said, it enables us to discover whether a set of obtained frequency differ from the expected. These are some of the features of this goodness of fit test. And we have an example here for preference of chocolate bar, where you have a sample of 120 people who were asked which of the 4 chocolate bars they prefer. Okay, so this is the hypothesis is we want to find out whether some brands or one brand is preferred over the other. That's the research hypothesis, also known as the alternative hypothesis. So for some brands, you want to also know whether if others are preferred over others, if you have the same, if all brands are equally represented, that will be your null hypothesis. But if others are not, then it is your research hypothesis. So in this case, the null hypothesis can only be true if we expect 30 for each category. So this is an example, and we have a table here providing the observed and the expected values for each. And by the time it was subjected to the chi-square test, we arrived at 73.33, and this was compared with the critical value. It was found to be greater than the critical value. So also our p-value was found to be less than 0.05. So we reject the null hypothesis and then conclude. So we have so many of these tests. We have the chi-square test for independent, that is for two variables. And these are some of the conditions for using this type of test. Okay. Let me go straight to the most important area of this presentation. These are basics. All what we've been talking about are parametric tests. We are saying that you can also, carry out hypothesis testing using non-parametric tests. And some of these are the Mann-Whitney that we all know. It is one of the non-parametric tests that is used in place of the independent sample t-test. We also have the Nicosin test for paired, for non-parametric equivalent of paired sample t-test. And then we have Kruskal-Wallis, the non-parametric equivalent of ANOVA. So now, this is where much interest is required. How do we perform hypothesis testing in machine learning? So machine learning, in hypothesis testing for machine learning, it involves trying to evaluate or validate certain assumptions about a model or a component. And this approach, the approach differs depending on whether we're talking about the glass box or the black box model. This distinction lies in the model's interpretability and how readily the internal logic can be understood. So for machine learning, our interest is generally, for those of us who must have worked on machine learning, you'll see that the whole idea is for the machine to learn from the data and then be able to make prediction. So in that case, our concern is to ensure that whatever it is we are predicting, the assumptions, are they clearly made? Do they meet the assumptions for us to be able to use that model to predict? Or those components of that model we are building, are those components, how do we test if these components are significant? That is where hypothesis testing is required or is used in machine learning. So just like we said, if you have in machine learning, you understand the data, you build the model, this is the step you must follow. After you learn from the data, you build your model, then formulate your hypothesis, and based on your outcome, you can continue to refine your model until you have a perfect model before you can predict. So basically what you are doing is you are trying to see if either the components of that model you've developed is significant or not, or that the assumptions of the model is fulfilled. That is what we generally do in machine learning. So like we said, we have different models these models can be the glass box and the black box. So the glass box, which is also known as the white box model, is very transparent. The internal workings are clearly visible for us to see. An example of this model is the linear regression that we all know, the logistic regression, and the simple decision tree. So these models, clearly, you see them. So if you are going to use machine learning, you are going to look at what are the assumptions of a linear regression. For instance, number one, we know that the error time must be normally distributed. So if you have your model, you should be able to test that assumption. Okay. And by so doing, this is where the hypothesis test in machine learning can be applied. Also, you can look at each parameter, the estimated parameters for the model. You can see, does this model contribute significantly to the model? That is also how machine learning is adopted, is adopting hypothesis testing. For these models, these are traditional statistical hypothesis tests that we can apply directly to the models. That's for the glass box. So how do you do that? You can test for the significance of the model, which I've said. You state your null hypothesis, state your alternative hypothesis, talking about whether the coefficient is significant. So for the null hypothesis, you have there, you can say, does the coefficient of a specific feature, the coefficient of a specific feature is 0. I'm trying to say, okay, beta 1, for instance, is equal to 0. We're saying that it has no effect on the target variable. Why the alternative can be that the coefficient is not 0, meaning the feature is statistically significant. You can also do what we call you can also adopt the use of model comparison tests, where you use the log likelihood test and the F test to check which model is better than the other. And the assumptions is that the validity of this test is often depends on meeting the specific statistical assumption, such as the normality of error or the absence of multicollinearity. Then we have the black box models. These are models that are opaque. Their internal decision-making process is not easily understandable by humans. They are common. This is a common characteristic of complex model, like the deep neural network and assembly methods. The traditional parametric hypothesis tests are not usually applicable here because these models do not have simple interpretable parameters to test. So the challenge is to evaluate the model's behavior without knowing its internal logic. So how do you carry out this kind of test? The approach is to shift from testing the model parameter to testing its external behavior using model agnostic tests. And how do you do that? You can use feature importance testing. This test is to determine whether a specific feature contributes significantly. Just as we've said, we want to know if one of the parameters actually contributes significantly to the model. How do you do that? You can, by permutating, just remove the model. You after removing the model, the parameter from that model, you make predictions and compare to the previous model to see which one performed better. Okay, you can also use the conditional randomized test, to assess the independence between an outcome and its features, giving all other features without relying on the model specification. For the black box model, we also have the explainable AI and hypothesis testing techniques, where we have new methods that combine explainable AI techniques with formal statistical testings. This explainable AI include the local interpretable model agnostic explanation, which is abbreviated LIME, and the sharply additive explanation, which is abbreviated SHARP. These are tools that provide local explanation for individual prediction by approximating the black box model with an interpretable one. So hypothesis testing here can be used to validate the stability and reliability of this local explanation. So you can also do overall model comparison, because if one black box model is better than another, okay, you can do that. Or you can compare a black box model with a glass box by the sampling method through the use of pair t-test or A/B testing. Now, you often encounter problems when using machine learning. And some of these problems are usually solved using what we refer to as multiple comparison correction. In statistical, this multiple comparison correction is a statistical procedure that is used to counteract the problem of inflated size, positive rates, the problem of inflated false positive rates that occur when conducting multiple hypothesis testing simultaneously. So without this correction, if you perform many tests, some are likely to appear statistically significant purely by chance, therefore leading to erroneous conclusion. For example, if you look at a standard hypothesis, you only set your significant level to be 0.05, which represents the probability of type 1 error. This alpha value holds for a single test, okay? But however, when you have multiple tests, the probability of making at least one type 1 error within the entire family increases dramatically. For example, like we've said, in one test, we are saying that the probability of a false positive is 5%. But if you have 10 independent tests, the probability is 40%. And for 100, it's over 99.4%. So this is a problem. So how do you solve this? You use the common correction procedures that were developed to solve this kind of problem. So these correction methods aim to control either the family-wise error rates or the false discovery rates. The family-wise error rates is the probability of making one or more type 1 error across all the tests. Now, the controlling procedures are more conservative and are used when a single false positive is unacceptable, such as in clinical trials and so on. Example of these family-wise error rates tests are the Beniferos correlation, and this is how it is done. The formula is you have an alpha, an adjusted alpha to be equals to, you fix your adjusted alpha to be equals to alpha over n, where n is the number of comparison. The application is your p-value is considered significant only if it is less than or equal to the adjusted alpha. The limitation is that its high conservativeness can significantly reduce statistical power, thereby making it harder to detect true effects. So we also have another of these tests, the Horn-Beniferos method. It is less conservative, but more powerful than the Beniferos correction. And this is the procedure for it. You order the p-values from the smallest to the largest, compare the p-values. If it is significant, you continue. You will continue until all p-values are no longer significant. At that point, the subsequent p-values are also considered not significant. Then you can also control using false discovery rates. The false discovery rate is the expected proportion of false positives among all the rejected null hypotheses. controlling procedure are less stringent than the family-wise error rates, and they are appropriate for exploratory research where many tests are performed and some false positive are acceptable. So the for this false discovery rate, we use the Benjamin Haupt procedure, and the procedure is to order the p-values from the smallest to the largest. You find the largest p-value such that you find this condition, and then you reject the all null hypotheses for which the p-value is less than or equals to the pi. The procedure offers a better balance between controlling false positive and maintaining statistical power compared to the beneficiaries, which is important for large sample. So how do you choose your correction methods? The choice depends on your research goal and the consequences of your type 1 and type 2 error. So for the family-wise error rates, we encourage you to use the Holmes method. It is best for confirmatory studies with a limited number of comparisons where a false positive is highly undesirable. For the false discovery rates, we use the Benjamin Haupt method. It is best for large-scale explanatory studies like in genomics or A/B testing, where I'm trying a set of candidates for future investigation is the goal and mixing two effects. So in essence, what we want you to know is that in machine learning, our concern is using the use of hypothesis testing is to ensure that the assumptions of our models are fulfilled at the end of the test, or the parameters for the model. We want to see whether these parameters are significant. So that is basically what hypothesis testing is in machine learning process. One, you ensure you want to test if assumptions of the model that you have adopted are fulfilled, and that each parameter of the model is statistically significant. So we've provided a more practice exercise for you to be able to go through, and then some readings. So thank you very much for your time, and thank you for listening.
Yeah, thank you very much, our facilitator and our presenter. We really appreciate you for creating time to present this great teaching workshop. We really appreciate you very much. So if you have questions, before we round up, if you have questions, please, you can ask your question. If you have any question, I think, just unmute yourself. If you have question, unmute yourself. I didn't mute anybody. You can just unmute yourself and ask question. The interesting part is the application of hypothesis testing in machine learning. Very, very interesting. At least many of us were learning a new thing about the modern way of doing hypothesis testing. So if you have question.
Sir.
Yes.
You
are welcome. Ask your question, please.
I want to appreciate our facilitator and presenter for the wonderful job he has done to hypothesis testing. I just want to implore him to please share the slides with everyone on the platform so that we can continue to interact with
Hello?
Okay. Well, she said that you should share the slide with us so that we can continue to interact with you.
Thank you very much. I'm sorry, the network fluctuated there.
Okay, you're welcome.
I said I'm hoping you can share the slides with everyone.
Okay, yes, I think the coordinator, okay, I'm going to, I've updated this particular slide. So I will still send it to the coordinator so that you would forward it to the facilitator in OAU. I think that
All right, all right.
By the time you should be able to get it, yes.
Okay, no problem. I'll be expecting it. In fact, Mohammed Rice has replied that the slide will be shared. So, HOD, can you give us a vote of time so that we can round up? HOD, Dr. Mrs.
Good evening, sirs. Good evening, sirs.
Oh, yeah.
Dr. Nila speaking.
Okay, you are welcome, ma'am.
Please, sir, we would like, you are in OAU, so I would like you to please help us about the basics, of machine learning in statistics from the very beginning, the basics in machine learning.
Okay.
If we can have from your department, if we can have something built from the basics.
Okay, so you'll be able to understand what is presenting now.
On YouTube, sir.
Okay.
Maybe on YouTube in your department. And we can now be distributing that YouTube link all over OAU and other universities.
Okay.
Machine learning in statistics right from the beginning, the basics.
Right from the beginning. They are like elementary, the introduction to machine learning.
Exactly, sir.
We will do that, sir. We will do that, ma'am.
And yes. AI, everything AI with statistics, sir.
Okay.
It's a new thing that is coming up in Nigeria, which we don't know how to do. So it will be good for you to start from the basic for some of us that don't know anything about it, sir.
Okay. We will address that. But, questioning a Google form was sent out sometimes ago, about 2 months ago. So we told people to indicate the area where they really want the training. And people indicated that area. That is what we are addressing now. But this one that you are mentioning, maybe that will be our next agenda. So, but there's a training on machine learning on October 10. There's a predictive analytic. Mohammed, am I right?
Yeah, we do have other workshop topics in the coming weeks. For example, next week I can announce here we will be having the topic of entrepreneurship in statistics and machine learning. We do have a topic on data cleaning, and we have a topic on data visualization as well. We do have another topic on machine learning and I think statistical analysis. Yeah, and there is one more topic, I guess. We have 6 workshops lined up, and those will be delivered, I think, every Wednesday, 3 p.m. West Africa time. So please join us.
Please have something for us from the basics, from the very beginning, that we be progressing.
For sure, we will ask our instructors to have something that's very basic, or at least suggest you some resources where you can get those basics.
Okay.
Thank you.
Yeah, okay. Then we will also, if you really want the elementary one, please, you can visit us in our department. You should be able to start something so that whatever they are teaching there, you will understand it. Any other question?
I'm from Useful Resource Material Group. You posted this there.
Yeah.
Professor
Thank you very much.
Rasunde.
Oh, Mrs. Onila, Dr. Mrs.
Yes.
Onila, you are welcome.
Thank
please
you.
put on let me see your face. Please put on your camera.
Sorry, I'm not.
Okay.
I'm not presentable now.
Okay. Yeah,
I'll see you later, sir.
No problem.
I'll see you on our group. So we usually take people from basics of everything, so that many of us in research don't know the basics about statistics. Now that AI has come up and machine learning in statistics is totally new too. So for those of us that are not in statistics, but we are researchers, I am in dermatology, health sciences,
Okay.
So, and we are all doing research.
Yeah,
so we
yes,
need to
I agree with
these things from the basics.
Okay.
So we need to learn it from the basics, sir. Thank you, sir.
Okay, we will surely address that. We will surely address that. Thank you very much. Any other question before the HOD? Are you still on the line, Dr. Adeji?
Yes, I'm here.
Yeah. Can you just give a vote on time so that you can round up?
I want to thank everybody, especially the organizers, Professor Mohammed, both Mohammeds, our facilitator, Professor Mohammed Tanimu, and the enablers, Professor Mohammed Rais and Professor Pavel. I also want to appreciate Professor Oloshunde, our very own Professor Oloshunde in our department, for anchoring this program. Thank you very much to everybody, and thank you very much to all the participants. At the Department of Statistics, we pride ourselves in the technical aspects of statistics and also the applied aspects of it too. So everything you have said, we have listened, and of course, we will work together with Professor Oloshunde to ensure that statistics is accessible to everybody who is interested in applying it to research. Thank you very much once again. Thank you, our facilitator. Thank you, organizers. Thank you, everyone. God bless you.
Thank you very much.
So next week, we are just like Mohammed Rais has said that we are going to have entrepreneurship in statistics and machine learning. So please join us the same time, 3 o'clock next week. I will circulate the link on the platform. I circulate the link on the platform. In fact, I received several complaints today. I will not repeat that. They said the flyer that I circulate, many people cannot click. They can't click the link to the flyer. So they are just asking me now that you send the link, the actual link, not the flyer again. I will correct that next time. So thank you very much for coming. So I wish you a nice day. Oh, well, a nice day. I don't know whether our facilitator, maybe they are in the night or the day. Well, whatever I have a nice day.
Thank you. You too.
So bye-bye.
Thank you.
Yes, thank you so
Thank you.
much.
See you
Thank
next
you.
week. Thank you.
Thank
Bye-bye.
you.
Thank you
Thank
very
you.
much.
Bye-bye.
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 Bye-bye.